Hi, Assalamualaikum. Good morning, everyone. I'm Hadaria Bahrun from University Technology Mara, Faculty of Applied Sciences. And today is my first lecture on CHM577, Inorganic Chemistry. I'm going to be covering in this lecture atomic radii, ionic radii, ionization energies, and electron affinity. The materials are prepared by the resource person of CHM577, Dr. Amalina Muhammad Tajuddin, and I'm going to present it for my class. So as a chapter outline, yeah, today we're going to learn how the periodic classification of elements come about, and students are going to be able to construct the electronic configuration of all the elements in the periodic table, and students are going to be able to identify the periodic variation in the physical properties of elements in the periodic table, which are the effective nuclear charge, which is ZF, the ionic and atomic radii, ionization energy, and electron affinity. As an introduction, this is the very familiar periodic table that everybody learning chemistry have seen so many times already. So this has come about through a long series of work by chemists from hundreds of years ago, and Dmitry Mendeleev had worked on the periodic classification of elements according to the properties of elements. As elements are discovered by scientists, they investigate the properties, and Mendeleev had tried to classify those elements according to their properties. And this is the most significant achievement in chemistry in the 19th century. If you look at the color pictures, the colored boxes here, you will be able to get some information when was that element discovered. For example, the ones in yellow, which are the elements at the very bottom here, they were discovered between 1965 to 1999, very recently discovered. But the one in gray, for example, iron, gold, and mercury were discovered in the ancient time. And then we have the purple, the lilac here in the 1700 and 1800, blue, which is a little bit more recent, in the 18 to 19, early 1900, and in the Middle Ages, they discovered these ones in green, the zinc, the platinum, phosphorus, astatine, and Sb and bismuth, yeah, and so on and so forth. So this is the time at which that element or have been discovered. Now, the periodic classification of the elements. I mean, when there are hundreds and hundreds of elements being discovered, scientists started to notice that there are some similarities between elements and there are some striking differences between elements. And they also noticed that there is a trend of elements, the properties or criteria of those elements. So the modern periodic table, as you see it in here, are arranged according to the principal quantum number of the outermost shell. N is the, so if we say N is equal to 1, we're talking about the elements in the first row, which is hydrogen and helium, where that is N is equal to 1. And then N is equal to 2 is the elements that are put in the second row from lithium to neon. Yeah, these elements from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And then you have N is equal to 3, which is the principal quantum number of 3, where the elements are said to have outermost electrons in the third shell. Yeah, the third shell where you find sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon, and so on and so forth. We go on to n equals to 4, n equals to 5, 6, 7, and we have here the actinides and the lanthanides series. Now that is going across the period. When we go down a group, this is called a group. When you have vertical arrangement, that's called groups. So in group 1, you have all the elements having the outermost electrons in S1. I'm going to go through this with you. In the orbital S, and there is one electron in S orbital. But for hydrogen, it is in the outermost shell number 1. For lithium, outermost shell number 2. But it's still one S electron in the orbital of S. Yeah, and S2 is also similarly where the electrons, the outermost electrons, occupy the S orbital, but pairing up with the S1 just now. And in here, there is this block, which is we call the D block. This will become very apparent later when we start going into electron configuration. This in here is the D block. On the right side here is the P block. So you have the S block. This is your S for, I don't know, what is S? Sambal? D and P. So we also have the F block down here. So that is all classification according to the location of the outermost electrons or the valence shell electrons. So just 1 second. Right. On the classification of the elements, of course, the S block here, we call them representative elements. The D block here, we call them transition metals. This yellow is actually in the D block, but they are not quite transition metals. They're simply called zinc, cadmium, mercury group. Yep. And this brown, just another the P block is also representative elements. So anything that is not in the D block is called the representative element. And on the very right hand corner or right hand side of the periodic table are the noble gases. These are the green, light green ones are the noble gases. And then down here at the bottom, if you look at the number, this is 57, lanthanum is 57, and cerium is 58. So it actually is a little bridge between 57 and 72. The location of this group of elements down here, which are called the lanthanides for the top one, and the peach at the bottom here are the actinides. They are actually located in this position. So periodic table is very, very long, very, very long from the left to the right, but they break the middle, just put it down here so it is easily represented graphically. So those are your classification of elements. So you have your representative elements for the S block and the P block. You have your transition metals for your D block. You have your noble gases at the very end on the right hand side. You have the actinides and you have the actinides and the lanthanides. So those are the classification of the elements. So from group 1A to group 7A, if you look at here, this is your group 1, 2, 3, 4, 5, 1A to 7A, they are known as representative elements or the main group elements. They all have incompletely filled s or p orbitals or subshells. Yeah. Group 8A, except for helium here, this is your 8. You can see. I'll go back. This is 1A, 2A, 3, 4, 5, 6, and 7. Yeah. Those are your representative elements. And then your 8A are the noble gases. Yep. Go back here. Let me make this slightly bigger. Maybe we can, make it slightly bigger. The 8A, they have the noble gases have completely filled p orbital. That's going to be very clear to you once we go into electron configuration. And then group 3B to 8B, this is the 3B, 4, 5, 6, 7, and 8B. These are called the D block. Yeah, D block transition metals. They all have incompletely filled D orbitals or D subshells, and they will produce cations with these incompletely filled D subshells. Group 4F and 5F, which are here, this is your 4F and your 5F, your lanthanides and your actinides. They all have incompletely filled F subshells or F orbitals. Yeah. So let me go through that. And we call those electrons arranged filling in the orbitals, they are in the ground state electronic configuration. That means they are not excited. We have excited state and we have ground state. So ground state, everybody stays where they should be staying. Yeah, very, very stable. It is an electronic arrangement described for each atom. And then we also have the Aufbau principle. Aufbau is a German word, means a building up principle. How do you build up electrons filling in orbitals in your elements? And they are used, the Aufbau principle or the building up principle are used together with the Hans rule. Hans rule is a rule on that the electrons will be, singly first, and then bila dah penuh, when it is full, then it starts to pair up, and Pauli's exclusion principle. So we'll go through all that later. So there are many, many new principles that you will be going through to understand the periodic table. Okay. In the ground state of the atom, electrons will occupy the lowest energy orbitals first. Now, this is very understandable, just like when you have a block of flats, a block of apartments. Usually, people will prefer to stay at the bottom, at the lowest level. So, because anything that is close to the ground is very stable. So by nature, we like to be stable. So same with electrons. Electrons will fill in the orbitals at the lowest energy level first. Once it is full, then the electrons start to go up to higher and higher and higher levels. And so that is very, very systematic. They will only fill the higher energy orbitals when no lower energy orbitals are left empty. So the order of filling of energy sublevels with electrons, you have 1s, 2s, and 2p. I don't know whether you have come up before this with this s orbital, p orbital, d orbital. I'm not sure. Have you? I hope so. So you have 1s orbital, and each one of this s orbital will only take in 2 electrons. So 2s orbitals, and then 2p. So you have 1s, 2s, and 2p. So in the first quantum number, you only have s orbital. In the second, you have s and p. In the third, you have s and p and d. Yeah, s orbital, p and orbital, d orbital. So you have in the second quantum number n is equal to 2, 2s and 2p orbitals. Now, when you go higher, you go to the quantum number of 3, so you start getting 2s, no, 3s orbital, 3p orbital, and 3d orbital. As you can see, the energy levels go up as you go further from the nucleus, because the nucleus is right in the center. Yeah, nucleus of your atom is right in the center, and you have the first shell. In the first shell, you only find one s orbital. It's called the 1s orbital. In the second shell, which is further away from the nucleus, yeah, the second layer, you have the 2s and the 2p orbitals. And then when you go to the third layer, which is further away from your nucleus of the atom, you have your 3s, 3p, and 3d orbitals. And as you go to the fourth layer or fourth quantum number, you have 4s, 4p, 4d, and 4f. So you might recognize this S. When I say S block, you remember the periodic table that we discussed earlier? S block, that means the last electrons are staying on an s orbital. The last electron to come in, it is staying on the s orbital. When I say p block, that means the last electrons that go into that element to make that element has occupied a p orbital. So that means it's staying in the p block. And then the d block, that means the last electrons would go to, yeah, the d orbital. And the f, the actinides, the lanthanides, the last electrons go to the f block. So if you can imagine, this is the nucleus. This is the nucleus of your atom. And then on the first layer or the first shell, you have S. So in come an electron. Ting, 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 ting. The electron comes. Oh, there is an empty orbital. So it goes into the first empty orbital. It goes to the S. So that is hydrogen. When you have one electron, then it is hydrogen. When you have two electrons, you have helium. You are building the electrons to meet the elements. So you have the first electron going in will make a hydrogen. The second electron going in will make helium. The third electron cannot go in the first shell, because in the first shell there is only one s orbital. So the one s orbital is full. They have to open a new village, they have to open a new layer, and in the new layer, which is on the second layer, ada S dan ada P. Now, S ada satu saja, P ada tiga. You have PX, PY, and PZ. So in the second layer, ada one S orbital, which is the 2S, and then you have the 2PY, 2P, X and 2PZ. So 4 orbital, that means ada 8 elektron boleh masuk. There are 8 electrons that can go into the second layer. So the third electrons that go in will make lithium. And lithium will occupy this 2s orbital. Yeah? So lithium. And then what next? The fourth electron. What is the fourth electron after lithium? Will make beryllium. So the fourth electron will, excuse me. I've gone too far. Have I? Yeah. So the fourth electron will occupy the 2s, making beryllium. And then the fifth, the sixth, and seventh, eighth, sampailah the electron number 10 that will make neon. So if you go back to here, so the fourth electron will go to the 2s to make beryllium. The fifth electron go in with S dah penuh, the 2s dah penuh, is full. So you have to go to the P. S is full, so P is available, so it will occupy PX. So that will make boron. And then it will go, the sixth electron will go into the PY. The seventh electron to make nitrogen will go into the PZ. The eighth electron will pair up with electron number 5 because the electrons will have to occupy singly first. That is called the Hans rule. Hans rule mengatakan when electrons want to fill in orbital, they will fill the orbital yang at the same energy level singly first. Single. After all of them full with single, then they start to pair up to make a pair of electrons with the opposite spin. So oxygen with 8, the number 8, electron number 8, will have that electron number 8 pairing up with electron number 5 in px, and then number 9 pairing up with number 6, and number 10, electron number 10 will pair up with electron number 7. So this, if this concept is new to you, you'll probably be a little bit confused, but do not worry. I'm going to go through it with you slowly a little bit later. Right. So you have to remember 2 rules. This is the 3 rules. This is the Aufbau principle. Now, when we start going into further away from the nucleus, when you go into the 4th quantum number, you will start to see that S4S is at the lower energy level compared to 3D, even though 3D is in the 3rd shell, tapi 4S has lower energy. And this is very common to happen when you move away from the nucleus. You will start to get overlapping of energy levels. Yeah. So that is, this talks about the Aufbau principle. And then the one that I'm saying, electrons occupy all the orbitals singly before the pairing begins. That is Hans rule. The unpaired electrons have parallel spins. Yeah, when you have them singly, they will have spin that is going north all. And then when it start to pair up, then you have the spin that goes south. Yeah, the spin opposite. And Pauli's exclusion principle says no 2 electrons in the same atom may have the same set of N, L, M, and ML, excuse me, and quantum numbers. So N is the quantum number, which is the shell. L describes your type of orbital, whether it is S, P, or D, or F. M describes your spin, either spin up or spin down. Yeah. So don't worry about that. So these are, if you like, this is actually the address of electrons in the periodic table. So macam kita kan rumah banyak, there are many houses in a village or in a terrace area or wherever. Each one house has their own address. So NL, ML, and MS, those are the addresses of the electrons, just like humans. Yep. So let me take you into this slide, which is the condensed ground state electron configurations in the first 3 periods. Okay, about the condensed ground state electron configuration in the first 3 periods. 3 periods mean, okay, this is not in your notes, so you can add them yourself. I have put all these drawings at the bottom just to illustrate, to make you understand the concepts of orbital, the concept of electron configuration, and so on. Okay. Now, when you have an atom, there is a nucleus here. The black one here is the nucleus. And then shell number 1, or N is equal to 1, is very close, or the first layer, that is closest to the nucleus. And in n equals to 1 or quantum number 1, you have only s orbital. As I was telling you, only s orbital. And s has only one orbital. Now, once the s orbital in here is full, the next electron coming in will have to open a new quantum number. And the second quantum number, n is equal to 2, which I color green here. N equals to 1 is color red. The green one is in n equals to 2. And as I was telling you earlier, in n equals to 2, you have s orbital and you have p orbital. Now, s orbital, again, only one box. P orbital has three boxes. So p-type has three orbitals. So if you want to make it understandable to, we will say S is like a rumah bungalow house. P will have to be maybe a terraced house with three terraced house. So px, py, and pz. And then once all these orbitals, the 1s orbital is full with electrons, the 2s is full with electrons, the 3 2p orbitals also full with electrons. The ninth electron number 9, when it comes, it has to open n equals 3, which is a new village or a new quantum number. So n equals 3, I color it blue here. This is n equals 3. I hope you understand this. This is the outer shell, the outermost shell of your atom. So in n equals 3, you have s orbital, p orbital, and d orbital. Now, S only has one orbital. P has three orbitals, the px, the py, and the pz. And the d orbital now has 5 orbitals. So you have dxy, dyz, dxz, dx squared minus y squared, and dz squared. And each of these are located in the quantum number as they are similarly colored. So this is in the shell number 1, only 1s. Shell number 2 are the 2s and 2p's. And then shell number 3 are the 3s, 3p, and 3d orbitals. And these are the orbitals that are arranged in increasing energy. So 1s is the lowest energy level, whereas the 3D will be at this present moment the highest energy level. Now, you have built the orbitals. How do electrons go and fill up these empty orbitals? Now, as you like, if you think of the orbitals as houses or places for electrons to stay, so when the first electron comes, which is for hydrogen, I take one of these electrons here. I can't take the electron. Yeah. It will go to the 1s electron. There you go. The 1s, one electron. So that is hydrogen. And then when the second, this is here, that's why it's called 1s1. Can you see it? 1s1. There is one electron in the s1 orbital, right? And then when the second electron comes along, it cannot be of the same orientation as this first one, because if you remember the Hans rule, electrons occupy all orbitals of a given subshell single. Once it is full with that, barulah they can start to pair up. So in pairing up, you have to take an electron of the opposite spin, and it will occupy the 1s. They should be a little bit closer. This is too far away. Yep. So the second electron will occupy the 1s orbital. It cannot go direct into the 2s because 2s is in higher energy level. Remember, 2s in kampung number 2, n is equal to 2. So that is your helium. So helium here is 1s2. In the 1s, there are 2 electrons. In the 1s orbital, there are 2 electrons. I hope you understand this. Now, what happens when the third electron comes along? Similarly, the third electron will come along, dum, 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 and then stay on the first available lowest energy level orbital that is empty. So it will go into the 2s. That is why lithium is called, now helium is 1s2, yeah? Helium is 1s2. You can call this 1s2, 2s1. But you can also put helium in square bracket here to indicate that full shell. So helium is a noble gas that represents a full shell. Yeah? So helium 2s1. And then the fourth electron cannot be going into the 2p. Why it cannot go into the 2p? Just 1 second. Sorry, where was I? There was a distraction. Okay, Hans Rule are saying that they will have to occupy singly before being paired up. Right, so we go into, so when the fourth electron comes along, yep, it will be of an opposite spin, and it will occupy the 2s orbital, and that is beryllium. Yeah, so beryllium has an electron configuration. This is the electron configuration of helium ataupun 1s2, 1s2, 2s2, or helium 2s2. And then when the fifth electron comes along, it will go into the first p orbital, right? The sixth one will not pair up with this one. Why? Because these 3 orbitals, these 3 p orbitals are having the same energy level. Can you see it there? That's the same energy level, all the 3 p orbitals. So that is boron. Then the next electron, which is electron number 6, is for carbon. It will occupy singly. So if you can see, boron here is 1s2, 2s2, 2p1. Whereas carbon is 1s2, 2s2, 2p2. There you go, 1s2, 2s2, 2p2. And then electron number 7 will also have to occupy singly the p orbital because there are 3 at the same energy level in that position. So number 7 adalah nitrogen here. So nitrogen is 1s2, 2s2, 2p3. Yeah, 2p3. Then electron number 8 will come along. Electron number 8 will come along. And it cannot be of the same spin as these 3 because they have to be of the opposite spin. So we take this one here to pair up with that one over there. Yep. And what is that? That is oxygen with 8 electrons. 8 electrons is 1s2, 2s2, 2p4. The next one for fluorine is pairing up that way. You get 1s2, 2s2, 2p5. That's for fluorine. 2p5 is 1, 2, 3, 4, 5. And lastly, untuk menjadikan neon, to make it neon, to make this shell number 2 complete is the last electron to pair up. So you have 2 electrons in the shell number 1 and 8 electrons in shell number 2. So that is how you build up to neon, 1s2, 2s2, 2p6. Can you see? 1s2, 2s2, and 2p6. Now, what about electron number 11? Where does it go? So electron number 11 again will repeat the same pattern, but will go on to shell number 3, which is shell number colored blue here, because the green is full, the red is full, so it has to be blue. Now these colors, I give it themselves, not any formal color given by any of the chemists before. This is for me to easy for you to understand. So we have electron number 11 for sodium goes into 3s1. So we say the valence shell configuration for sodium is 3s1. And then the next one, to make magnesium, it has to be of the opposite spin because it cannot start occupying the P like that. So that's 3s2, neon 3s2 for magnesium, neon 3s1 for sodium. And then 3p, you have aluminium like that. And then silicon. And then you have phosphorus. After phosphorus, then all the p orbitals of the 3p are singly occupied. So it's ready for receiving the opposite spin electron. Sulfur is 2p4. Yeah, 3p4. Sorry, sulfur is 3p4. Then chlorine is 3p5. And argon is 3p6. So 3s2, 3p6 is for argon. So you complete the third shell of S and P. Remember, we also have d orbitals for this one. But the d orbital, as you can see here, the d orbital is located higher than the 4s. So the 4s will fill in first. But that's later. I'm going to cover that later. Because if you have a look here, yep, this we talk about up to argon just now. So the next one, electron number 19 and 20 will go to the 4s first here. Yeah, because 3p has been full, so you go to the 4s to accommodate electron number. What was it just now? Electron number 19 and 20. 4s for electron number 19 and 20. And then electron number 21 will start to fill in the 3d because this is the position, this is the energy level that we are talking about. Yeah. After 3p is complete, you start filling in 4s. After 4s is complete, you start filling in 3d. Then when your 3D is full, you start filling in your 4P, 4D, and 4F, and so on and so forth. So I hope you understand how electrons are filled up. So remember, even though S, P, and D here are in the same shell, you have the 4S occurring somewhere between the P and the D. So your 4S will have to be filled in first. Yeah? So I hope you understand that. Let me this. Yep. And what's next? Right. So electron configurations of anions and cations. Okay. When the atoms are in neutral position, for example, sodium is neon 3s1. Remember? Sodium is neon 3s1. It's here. It's this electron 3s1 there. When it will undergo ionization, the outermost electrons or the electron at the highest energy level will be removed first. So you have losing electron of the 3s1 will make sodium plus. Losing electron on the 4s2 will make calcium 2 plus, and losing all the outer electrons of aluminium, which is 3s2, 3p1, will make aluminium 3 plus to reach the configuration of noble gas, outer shell. So go back here. For when sodium loses the outermost electron, it will become a neon. Yeah. When magnesium loses 2 electrons, it will look like a neon. When aluminium loses 3 electrons, it will look like a neon. So what is the purpose? What is the octet rule? Octet rule actually states that all elements will try to look like the nearest noble gas. And all noble gases have filled shell, except for the helium. All noble gases has 8 electrons on the outer shell, 2s2, 2p6, 3s2, 3p6, 2n6, 2n6. So losing the electrons for metals and gaining electrons for non-metals will make the element look like a noble gas. Yeah. So all metals will lose electrons to imitate or to resemble a noble gas, and all non-metals will gain electron. The metals will lose electrons, whereas the non-metals will gain electrons. Now, how do you know what are metals and what are non-metals? Let me have a look in this. Yeah. So you have aluminium. If you remember, there is like a step situation here where everything under here, all of these are metals, and at the top here on the top right are all non-metals. So non-metals will gain electrons to achieve stability or to look like a noble gas, whereas metals will lose electrons to achieve stability or to look like noble gas. So atoms gain electrons so that anion has a stable noble gas outer electron configuration. For example, hydrogen will have to gain hydrogen will have to gain 1 electron to look like a neon. Fluorine will have to gain 1 electron to look like, that hydrogen to look like helium, sorry. And then fluorine, oxygen, and nitrogen will have to gain this one 1 electrons, 2 electrons, and 3 electrons to look like the closest noble gas, which is neon. That is why you get metals to become cation and non-metals to become anion. Yep. I have given you a 45 minutes lecture for now. I'm going to stop here. My next lecture will be on this one. So this series, I'm going to stop at this slide number 9. So take a rest and then continue on the next lecture. Thank you. Bye, everyone.